Hello guys, welcome to LeetCodes, and in today's video we will discuss LeetCode question 662 that says maximum width of a binary tree. So guys, here you are given the root of a binary tree and you need to return the maximum width of a given tree. Now the maximum width is defined as the width that is maximum among all the levels, and for a particular level a width is just a difference between the leftmost and the rightmost non-null nodes, the length difference, right? It is guaranteed that the answer will be the range of 32-bit signed integer, so it will be stored in an integer. Now let's take this example. So here if you take a node at this level, so this is a level 1 or level 0, whatever you can say. What is the width of this level? The width is 1, right? There is only one node, so the width is 1. What is the width of this level? The width is 2. What is the width of this level? See, there is node 1 node, second node, third null node here is there, and fourth this node. So there are 4 nodes, so width is 4. What is the maximum among all the width? 4. So yeah, we written 4 as our answer. Now if you take a look at this example, here the width is 1, at this level the width is 2. Now here just make all the null nodes also. I am creating the null nodes, so it is better to visualize. So here the width is 4, here there is one null node will come. For this null there would be 2 nodes, for this there would be 2 nodes, and here it would be 1 node. Now here this is not null nodes and this is not null node. And what is the width between these two? This is 7. See, 1 2 3 4 5 6 7. So there are 7 nodes, so the total width at this level is 7, because the length between two not null nodes is 7. So yeah, this is the width, so that's why we written 7 here. Okay, got it? See, this last null nodes is not counted because we need to count the length between two not null nodes. So that's why between these two nodes only, and that is 7. So we written 7 here. Okay, and here the width at this level, level 2 is 2, right? But the width at this level 3 is 1. There is only one not null node, so the width is 1, right? So this is the maximum width at this level, right? And that is 2. So yeah, we written 2 as our answer. So guys, till now what we are doing is we are checking the width at each level. What we are doing? We are checking width at each level. So since we are checking the width at each level, level wise, so this is level wise traversal, we require level wise traversal, and that's why here what we can do is we can do breadth versus, right? Breadth versus is nothing but a level wise traversal. Now another thing that we need to figure out, that how can we find the width at each level? How to find width? We need to figure this out, right? Now let me again take one example here. So guys, given this example, how you will find the width at each level, right? Theoretically you can do like this, means visually it is easy to find the width, but in real situation how you will find the width? So for that, let us do one thing. What we can do is we can number the nodes. Let's say numbering, I am starting the number from 0, numbering this node to 0, 1 2, then 3 4 5 6, then 7 8 9 10 11 12 13 14, right? Here this would be for 8, this would be for 9 and 10, this 5 will be getting this 11 and 12, and this 6 will be this. So if you have some numbering like this, then you can easily do what? You can easily do the subtraction. That is 13 minus 7 is nothing but what? It is 6. It is 6, right? So the difference is 6. What is the width? It is 6 plus 1, so that is why the width is 7. So everywhere if you want to find width at each level, what you can do, you can simply subtract these numbers, right? 2 minus 1, and into here 0, and add 1 to all. So so by doing this calculation, you guys can figure out that what is the width at each level, correct? So once you number the nodes, you can figure out what is the width of the level. Now, so now now you have understood how to find the width. What is our next question? Our next question is how to number the nodes, how to give numbering to nodes. Okay, this is our next question. So here we had followed the sequence like 0 1 2 3 4 5 6 7 8 9 10 11 13 14. But is there any other way that if we won't follow the sequence, we can give the numbers directly from the parent? So yeah, if so there is one formula for this. So if the parent if the parent index or number you can say is I, then for its left child the number would be 2 into I plus 1, and right child would be 2 into I plus 2. Okay, so you can verify here. See here, the parent number is 1, right? Parent in I is 1, so its left child is 2 into I plus 1, that is 2 plus 1 3, and its right child, this is 2 into I plus 2, so that is 4, right? So that's why you can verify that this formula is correct if the parent index or a number is I, its left child is 2 into I plus 1 and right child is 2 into I plus 2. Okay, so basically talking about this formula, why 2 into I? Because given a binary tree, it has two children at max from each parent, right? So also you can see that at each level, so at a level 0, what is the width? It is 1. Level 1, what is the width? 2. Level 2, what is the width? 4. Level 3, what is the width? 8. So maximum width I am talking about here, it is 8. So as you can see, this follows the a power of 2, let's say n. So as the height, or you can say the depth of the tree increases, the number of nodes at each level increases by a power of 2, right? So since we follow this pattern, since binary tree follow this pattern, we can say that this formula is valid, that is 2 into I plus 1 and 2 into I plus 2. Okay, so till now we have cleared that how to find the width. So with that, for that we are giving the numbering, how to give the numbering. So from this parent I, we can give the numbering like this. Okay, clear till here? Now let's give a numbering. So guys, let us give the numbering starting from 0. So this is 0, so 2 into 0 plus 1, this would be 1, and here 2 into 0 plus 1, this would be 2. Now here this is 1 and this is 2. Now based on the formula 2 into I plus 1, so here it would be what? It would be 3. Here it would be what? 2 into I plus 2, this is the right child of this, so 2 into 2 plus 2, 6. Okay, now here 2 into 3 plus 1, since it is the left child, so plus 1, so its answer would be 7. And here what is the index? What is this value? So it is 2 into 6 plus 1, 13, right? We get 13, right? We directly get this number, so 13 and 7, right? So yeah, by using this formula we can directly get the answer. So guys, if I tell you that we can represent all the numbers or that we are numbering here in the form of 2, like 2 into 0, then 2 into 0 plus 1, 2 into 0 plus 1 plus 1, then here also 2 into 2 power 0 plus 1, so this is nothing but 3, and similarly 2 into 2 power 0 plus 2, and here also 2 into 2 power 1 plus 1, 2 into 2 power 1 plus 2, so this is nothing but 6, right? So similarly here 2 into 2 power 1 plus 2 plus 1. So if we do something like this, then we can see that this is nothing but a power of 2. This is power of 0, then power of 2 power 1. Then if you move on, then you will get 2 into 2 power 10 at some point, and at some point you will also get 2 into 2 power, let's say 100 plus something, right? See, now at each step, see, this is level 0, level 1, level 2, level 3. At each level the power of 2 will increase, okay, in the calculation. So let's say at level 1400 you might get something like this, 2 into 2 power 14, let's say 1300 something, 1300 something plus something. So this value will be very large. This can be very large, right? This can be very large. For an example, so guys, for an example, if you have something only 2 nodes like this, only 2 nodes, right? At each level only 2 nodes, at the leftmost and the rightmost end 2 nodes, something like this, only 2 nodes up till the end. So how many total nodes here possible? Total nodes here possible are 1500, and total nodes here possible are 1500, right? Why 1500 only? Because if you look at a constraint that there can be total 3000 nodes, so on the left child there can be 1500, on the right child of a root there can be 1500 nodes. Now if you apply the numbering, so this can be very much less, like 2 into 2 to the power 1400 something plus something, 1400, let me take 1400 only. So this is very large. This can be stored, this can't be stored in the integer or long or even long. This value can't be stored, right? So if you apply this current numbering strategy, if you apply this strategy, and if you encounter some tree like this that has only 2 nodes at each level, at that point the height, or you can say the depth of the binary tree, will increase to so much extent that the value, or 2 to the power something, this value will be so large that it can't be stored in the int, long or anywhere. So this is the problem of integer overflow. So this is nothing but integer overflow, and we need to solve this. Okay, we need to solve this problem, right? So now guys, how we can solve this question, how we can solve this problem, to solve this question? So what you can do, one thing is, so guys, to solve this integer overflow problem, what we will do is, we will start numbering the each node from 1 only. So this would be also 1, then this would be 2, then this would be 3, this would be 4, this would be again 1, then 2, 3, 4, 5, 6, 7 and 8. Okay, so we would start numbering the nodes at each level from 1 only, and that's how we will solve this question, right? Now let's move on to the coding part, where we will see that how we will handle this numbering part and starting the number with 1 only. So guys, here I have taken the same example, and what I did is I initialized the queue with the root node as well as the index with a numbering 0. So this is 0 numbering I have given. Now for this is where I am storing the left shell and the right shell along with the index. See, this is the loop where I am starting for all the nodes present in the current queue, and after that I am here calculating the index of the parent. So for that calculation of the index of the parent, what I am doing is I am taking the current node index minus starting node index. So here the starting node index is 0. See, here I have stored the starting node index, right? That is for the first node at the present of the queue. So this is 0, starting node index is 0. So yeah, when calculating for this node, what is the front node index? So it is 0, and starting node index is also 0. So this is 0, and 2 into 0 plus 1, it is 1. So I have numbered this node as 1, and similarly the right node would be 2, because I am adding 2 here. Now take a look at here. For the next loop, when calculating and storing this node, what would be the starting index? Starting index would be 1, and what would be the current node index? So this would be the current node, right? Present here, present at the topmost. So it would be 1 minus 1, that this would be 0, right? So again this node would be numbered as 1, because this index value would be 0, because the current node index is 0 and starting node index is also the same, right? So subtracting them would result into 0, and that's how we will start numbering at each node for each level from 1. Okay, if you are calculating the index for this node, so its parent is 2, right? Its parent, or this value is 2, and the starting index is 1. So 2 minus 1 is what? 1. So what it would be value? 2 into 1 plus 2, this is 4, right? So isn't this the current numbering? Yeah, 4 is the current numbering, because there would be one node of number 2, one with a number 3, and this would be 4. So yeah, 4 is the current numbering. And similarly this node would be start with a number 1. Okay, the starting would be from the number 1, and here for this node its parent number is 4. So 4 minus what would be the starting index? Starting index would be 1. So this is the 3. So 2 into 3 plus 1, this is what? 7. So yeah, 7 is the correct number, right? So guys, this is how we will always start the numbering of nodes from 1, and then we will number. So this subtraction will help us to prevent the integer overflow and start numbering from 1 itself for each node at each level. And at the end, what I am doing is I am taking the difference of the maximum index and the minimum index. So yeah, before storing the indexes, I am also taking the values of the maximum and minimum index, right, here in these two variables, and subtracting them we will get our width at each level. So yeah, that's how I am storing the maximum width at each level in this width variable, and at the end we will return this width variable. So yeah guys, that's all for this video. Now talking about the time and space complexity. The time complexity here would be big O of n, since we are traversing all the nodes of a given binary tree, and the space complexity would be nearly, you can consider to big O of n, but this would be the maximum number of node at a level. So let's say there are 5 nodes at a level, so that would be the space complexity. because at a time we are storing all the nodes that are present at a particular level, right, inside this queue. So that is our time, that is our space complexity. So yeah guys, that's all for this video. If you guys have any doubts, then do let me know in the comment section. Make sure you like this video and subscribe to our channel. Thank you.